Now that we have practice working with different conic sections, looking at their graphs, the various attributes, and the equations, we're going to focus on the geometric applications of conic sections. And first, we're going to start with parabolas. So what I want to do is I want to sketch a really rough graph of a parabola. Looks something like this. Of course, my drawing's not perfect. Your drawing's probably also not going to be perfect, but that's okay. Now, we talked about how a parabola was defined as the set of all points such that the distance between a point on the parabola and the focus was the same as the distance between that point and the directrix, a line. And that is an important geometric property, but what we're going to focus on right now is actually a reflective property of parabolas. So a parabola is a curve that also has a very particular reflective property. If we draw in the focus here, the property of parabolas is that any light wave or sound wave that comes in towards the parabola perpendicular to the directrix gets reflected off the surface of that parabola directly into the focus. And it doesn't matter where that light wave or that sound wave is coming, so long as it's perpendicular to the directrix, it will get reflected off and into the focus. So I'm going to draw a few more just so we can see how this works. And of course it works from the other side as well. Now, because of this reflective property, parabolas are used in many real-life situations where we need reflections to happen in certain ways. And the most common example of this is actually a satellite dish. Now, satellite dishes on Earth are generally pointed in the direction of a satellite that's orbiting Earth. And what happens is the satellite that's orbiting Earth sends signals directly at the satellite dish on Earth. And what happens is those signals hit the satellite dish and get reflected to the receiver, which is located at the focus of that parabola. Actually, because it's a three-dimensional version of a parabola, we call that shape a paraboloid. But that's for calculus. That's a little bit more advanced. So what we're going to do is we're going to look at an example problem that involves satellite dishes. And then in the next video, we're going to look at another example that involves solar furnaces. And this is an example of a solar furnace I saw in Uzbekistan. It's a really, really neat situation, but we're going to save that for the next video. So right now, let's take a look at an example problem involving satellite dishes. A reflector for a satellite dish is parabolic in cross-section with the receiver at its focus. The reflector is 1 foot deep and 10 feet wide from rim to rim. How far is the receiver from the vertex? So we're told that the reflector is parabolic in cross-section. What that means is that if we look at a slice of it, then that shape is going to be a parabola. And so we're told that the reflector is 1 foot deep and 10 feet wide from rim to rim. So what that means is that this total distance is 10 feet. That's the width from rim to rim, and that the reflector is 1 foot deep. So this particular drawing isn't quite drawn to scale, but we get the idea. And we want to know how far the receiver is from the vertex. So we know that there is a receiver somewhere up here, and we want to know the distance from the receiver to the vertex. We want to know this longer distance. 1 foot is the shorter distance, but we're looking to figure out this longer distance. Now, we have a parabola here, and we're going to make life easier by deciding that the vertex is at the origin, like all of the parabolas that we've dealt with, and we need to figure out what the equation is for this parabola, because once we know the equation, we'll be able to figure out how far away the receiver is, or the focus, from the vertex. Now, we also can figure out the coordinates for these 2 points. Because we know the reflector is 1 foot deep and 10 feet wide, we can say that this side of the reflector is located at 5, 1, and the other side is going to be at -5, 1. That gives us a distance of 10 feet in between them, and then 1 foot deep. And so we know that a parabola that has a vertex at the origin and opens upward has the equation x squared equals 4py. And because we know the point 5, 1 is located on the parabola, we know that 5 squared equals 4p times 1. Since the point 5, 1 is on the parabola, if we substitute in 5 for x and 1 for y, we know that that has to be a true equation. And what this does is it allows us to solve for p. So this becomes 25 equals 4p. And if we divide both sides by 4, that tells us that p is 25 fourths, or 6.25, either way. And remember that when we have a parabola with equation x squared equals 4py, the distance from the vertex to the focus is given by p. And in this case, we've seen that p is 6.25. So we're asked how far is the receiver from the vertex. We can say the receiver is 6 feet from the vertex. So if we were to go and redraw this, I'm actually going to draw it a little bit wider because we know that the rim is 10 feet and we know that that depth is just 1 foot. And since we know the receiver is actually 6 feet away, it's going to be out fairly far. And so if we were to try and draw what this satellite dish would look like, the receiver would be up at the top, and then of course we have to draw the parts that connect the receiver with the reflector, and it would look something like this, and this distance would be 6 feet. Each of these distances on the side would be 5 feet in each direction, and then this distance down here would be 1 foot. So in total, the receiver is 6 feet from the vertex. And this is important because if we were building a satellite dish and we put the receiver too close or too far away, then those signals would not be reflected to the receiver. The receiver would be in the wrong place, it wouldn't catch those signals, and the satellite dish wouldn't work.